All right, welcome everyone. I hope everybody had a good evening yesterday, getting to practice a little bit of regex. And today we're going to go into, well, why did we even learn regex yesterday, right? I mentioned the process that normalizing data is important, but we're not working within a CSV data file anymore or just working with something like images. Instead, we're actually starting to work inside of the NLP process. Well, in the NLP process, we have it to where our entire text file is our data. We're not necessarily creating features and labels just yet. We're just worried about the purity of our data in this case. And what we're doing here is inside of this text file or this data file, we're going to cover the process of normalization or making sure that our text is tokenized, broken up into independent chunks that we can actually work with and normalized so that we have good data coming out the other end. Let me actually just copy this portion here. Bring it over to a new page. All right, so like I mentioned, we have a data file here. Oh, hello. Take your data with you, data file, that we're going to feed through the process of normalizing. That way we can ensure that what comes out the other end is some good readable data that we can utilize to later on train our chatbot and teach them how to make decisions and return information. This process is going to be diving into the text processing or text pre-processing portion. It is the prepping of our text file. We're not necessarily doing anything that's teaching or learning inside of the machine spectrum. Like we're not doing deep learning principles or machine learning just yet. We're just simply worrying about this is a text file that I have. I want to break it up and make it into something that I can read. Well, what we're going to be talking about today, it's going to be the process of, again, text pre-processing. And here we can see a small cycle here. We would start with text removal, making sure that all of the text inside is kind of flattened. Right? What I mean by flattened is we'll go into punctuations, maybe there's HTML tags, maybe the data that you're grabbing is coming from a web scraper, and that's the reason why you need to worry about HTML tags. Anything that's not useful information for your model would get removed in that text removal portion. To include something like pet words. If somebody was to take the Zoom script from today and try to break it down, there would be timestamps. There would be a redonkulous amount of pet words that I use, such as and every now and then I do say huh. So those would definitely show up. I know for a fact I say so pretty often, so that would show up inside of that text script quite a bit. And all of that would need to get removed in order for my model to be able to utilize my text file as proper data. Then there's the process of stemming. All right. Well, the process of stemming is where we break down words to remove suffixes. For example, running would turn into run. We would remove the ing at the end because that's what gets added into the word to try to bring it into context. We're going to try to break down the word to its purest form. Now, when we try to break down the word to its purest form, That would then take us to lemmatization. And lemmatization is we're not just breaking down the word to its truest form or trying to break down the word to its original form. In lemmatization, we're trying to break it down to where we truly understand where the word originated from. So the root of said word. Now, lemmatization is will treat every single word as a noun unless specified that it is not a noun. And in order to make that work properly, we need to conduct something called POS tagging. Now, tagging stands for part of speech tagging, meaning, hey, is this a verb? Is this a noun? An adjective of any sort? And that's what will allow lemmatization to actually break down the word and try to find its truest meaning. And then finally, tokenization. Well, actually, we will likely start with tokenization. We could start with either text removal or tokenization. I think those two are going to be interchangeable in my eyes, right? You could just do text removal without having to iterate through an entire array and then applying the regex for each array. Or you could just look through the entire text at once utilizing regex. Well, the concept of tokenization is trying to turn everything into a token, right? Think of your text block as a massive block of metal that you're trying to work with. Well, we don't want to necessarily try to teach our model how to learn by feeding it this entire block of metal. Instead, we want to feed it small chunks at a time so it can actually digest it, be able to learn from it, and create meaningful connections from it. Well, tokenization is a process of breaking down a massive amount of text into small chunks. And then once we have those small chunks, we can apply all of these concepts one at a time into each part of the text, whether it's sentence tokenization or word tokenization, before being able to feed it into our model. Now, those were a lot of keywords and a lot of terminologies that we haven't necessarily covered yet, and we will cover them here shortly as we move through our class today. I saw a hand go up. Go ahead, Carlos.
Real quick, you mentioned stemming takes away suffixes. Does it remove prefix? 'Cause I mean that would change the entire definition.
I believe it does as well. We're gonna see a couple of examples here shortly. And you're right, it does remove the entire, it can alter the entire definition. And because all these tools are going to be utilizing are built in, they're not necessarily built to match your specific needs 100%, right? They'll meet like 90% of what you need, but you may get something like some type of misbehavior. I think a common misbehavior that you see with stemming is was will turn into WA, as in what, and then it doesn't, at that point the model is like, well, this isn't an actual word. I don't know what to do with this, right? And that's where lemmatization comes in. So after we conduct stemming, lemmatization is a way of balancing it, saying, oh, okay, these words are no longer meaningful because of what we did with stemming. So we're going to get rid of these words and use the ones that are still valid after stemming to teach our model. Does that answer your question?
Yes, sir. Thank you.
Of course. All right. Any other questions regarding this overview of uh, text pre-processing? All right. If there are no questions, then the next concept we're going to be talking about is going to be noise removal with regex. Now, what is noise? Well, I'm sure a lot of people here have, since we're all veterans, I'm sure a lot of people here have tinnitus, right? And the way I think of noise is of something that doesn't allow me to concentrate, right? When I get really high noise or high frequencies that are going on here in the house, it becomes harder for me to be able to concentrate to accomplish my job. Well, that's the same thing with the model. The model is trying to learn as quickly and efficiently as possible. But it can't do that if it's receiving a bunch of background noise inside of the data that it's receiving. So here we see an example of a very short sentence here, as in who was partying. And then the first thing we do is we lowercase and we perform a little bit of noise removal. And you'll see a bit of a change between those two, right? Now, this noise removal is definitely up for context. For example, In this image here, we can see that they flattened it, meaning that the entire text is either lowercase or uppercase. Totally up to you to decide how you want to do that. Also, just keep in mind on the way you're training your model or what your model's intent is. So if your model is a simple guide that is, or excuse me, if your chatbot is going to be a simple guide that's just going to help people maneuver through a menu, something like a rule-based chatbot, then this probably works, right? We probably want to just remove question marks. We could get rid of capitalization because our rule-based chatbot is not really going to need to formulate answers or understand the user's intent or punctuation or uh, try to relate to the user in any sort. It's just going to essentially receive input, feed it through a decision tree, and then return an output. So in something like that, this would work. We could even remove question marks. But if we were working with something like a retrieval-based chatbot, well, then at that point, capitalization becomes very important, right? We need to be able to know what's important to the user. We need to be able to identify acronyms. We need to be able to identify why things are capitalized, right? To clarify intent behind the prompt. And that question mark may also be extremely important since the difference in meaning between a question mark and an exclamation mark could change the meaning of the entire prompt altogether. Then it breaks it down to tokenization, where it just breaks our string here of who was parting into a small series of who was parting, right? So we see instead of getting an entire string, we're breaking it down into small chunks that we can work with. And then in this case, they decided to use lemmatization and skip the entire stemming process. We'll see a decision base as to why to do that. You could do both, or you could choose to do one or the other. And then here we see who the party, right? So after this was lemmatized, it broke it down to the entire root of the word, the real meaning of the word. Who still means who, was is now be, and parting turns into party. We'll take a look at a couple of examples as to the difference between um, lemmatization and stemming here shortly. So that's just a brief overview. Let's go ahead and do a little bit of reading here. Can somebody read this paragraph other than Nick?
What is noise and why is it important to remove noise from text input? In the context of text pre-processing for AI chatbots, noise refers to any irrelevant, redundant, or inconsistent elements within the input text that do not contribute meaningful information for understanding user intent or generating a response. This can include typos, unnecessary punctuation, HTML tags, excessive white space, filler words, irrelevant symbols, or inconsistent casing. Removing noise is crucial because it helps ensure that the chatbot focuses on the most important parts of the input, reducing confusion and improving the accuracy of tasks like intent recognition, entity extraction, and response generation. By eliminating noise, we make the data cleaner and more consistent, allowing machine learning models to learn better patterns, generalize more effectively, and deliver faster, more reliable, and contextually appropriate responses.
All right, awesome. Thank you so much. Let's start working with this. Here we see a couple of examples. We have some excess punctuation examples, why it's considered noise here in the table. You can see it really adds no value or meaning, especially once we go into the process of tokenization. It's going to break it up so that each exclamation point or each one of these punctuation marks will actually turn into their independent portion of the list. We have typos and misspellings, especially after we do our stemming and lemmatization. It's not going to be able to recognize this information. So it's just going to throw it out of the bag. All right. It's going to say, all right, well, I don't know what these are. So they're just going to confuse me more than anything. And instead, it gets rid of it. HTML tags. So if we did something like scraping, we want to make, or even if you're working with a markdown file, right? You're going to remove special characters or these div tags. When you send code to something like ChatGPT, it might have like a decision based trying to figure out if these specific or yeah, when you said code, it might try to figure out if these HTML tags are to be kept or not and have some sort of decision making inside of it. There's excess white space there, like I need help. There's case sensitive, so help versus help and help. So it can cause the model to treat identical words as different, reducing accuracy if normalized. Emojis are a huge pain because emojis are actually identified by regex through a UTF code. So if you want to do some sort of regex that will remove all emojis, you would have to essentially preload a redonkulous amount of UTF code and then go through the entire text to remove the emojis. But you definitely don't want those emojis to go into your model since, again, they're not words, they're UTF codes. Here we can see some filler words, URLs that really have no relevancy, right? If our entire chatbot is not required to understand URLs, then why even receive them? We have stop words in some cases. So the, is, at, or on, or in, common words that generally don't help identify intent or key entities in basic natural language processing tasks. All right. Now that we've seen a couple of examples and understand why they're considered white noise, does anyone have any questions regarding noise? Perfect. If no one has any questions regarding noise, then let's go into a little bit of practical application here. So here we have our text processing. I'm going to go ahead and open this up. And here we're going to talk about noise removal. We're going to go ahead and do this with regex. Now, in this next code block here down below, I'm actually going to get rid of this one. I want us to go through the process of opening a text file. I'm just going to say a file and reading its content to interact with it. We want to take a look at the file to identify possible dirty text. And then we will utilize regex to remove this text. All right. So this is our task for this portion. Well, here we have this full stack quest file. We can go ahead and open it up in a way that looks nice and pretty. So in a way that it's being displayed, we can see the letters are being bold. We can see there's a couple of italicized letters. As I scroll down, it looks like we have a series of dashes as well being added in here. So a couple of different stories that are in there. All right, it looks like dashes are going to be a problem in here. Let's take a look at the file at its purest form. So here's the file in its purest form. What do you guys think would be considered noise for a
The
model?
asterisks, making things italicized.
Yeah, so every single time we see an asterisk, so there's something to take note in, right? So maybe we want to start annotating this. Let's say, hey, we have asterisks inside of our notes. We have dashes inside of our notes. What else?
Commas, periods. I saw some double quotes, colons.
All right, so let's remove some double quotes. I think we'll keep, I think I want to keep the commas for now. Actually, let's remove them. Yeah, why not? Yeah. Let's go ahead and remove punctuation basically. So we have commas, we have periods. You said exclamation marks. Oh no,
I
you
saw question mark. I saw double quotes.
quotation marks, double quotes. All right. There's a slash there as well. So we want to make sure we identify that slash. All right. If I scroll all the way to the top, well, here at the very top, we can see there's also a pound sign there
And some emojis.
and some emoji. So here's the fire emoji. It won't even let me paste it. Hmm. All right, so I'm just gonna go ahead and put fire emoji. Perfect. So then we have the text that we want to remove. Well, let's take it one step at a time here. First, I want to read said text. So I'm going to go ahead and say file is going to be equal to open. And what I'm going to open, I'm going to enter the path to the full stack quest.md. I'm then going to read said file. And then finally, I'll close my file. Let's go ahead and take a look at text and see what that returns. All right, so text has been logged there. I can see the entirety of my text now as just one singular string from left to right. Fantastic. Now I want to break up this string, or excuse me, I don't necessarily want to break up the string, but I do want to remove all those special characters that we mentioned. Well, how can I do that? I know that I can write regex to be able to find matches, but is there a way to utilize regex to remove this
You
content?
can you can use the replace functionality and just replace it with nothing.
All right, so there's the replace functionality. Okay.
Roger said sub.
Yeah, and there's also the sub functionality. So in this case, we're going to go ahead and utilize sub. All right, so let me go ahead and open up a markdown here and say we will utilize regex dot sub method, which stands for substitute. The values we have identified as noise. All right, so let's go ahead and create that. Let's create our regex criteria or our raw string. Here in our raw string, we're going to start off with R, and I want to identify a couple of pairs there. For example, I know that I want to remove all of the R's. I mean, all of those asterisks there. So let's just apply that first portion. It's a clean string be equal to RE. Oh, I probably want to import RE, otherwise I won't have access to it. Dot sub. This method takes in 3 arguments. Where the first argument is the raw string to look for. The second argument is the string to substitute matches of the raw string. And then finally is the string to look through to apply substitution. So here we have our raw string, we have our clean string, and we can apply, well, the first thing is going to be my raw string. Then it's what I want to do to replace it. Well, in this case, I want to replace it with nothing. And then the text that I want to look through is going to be text. All right, that's how we saved it up here. We have text. Let's go ahead and execute this block of code there. All right, so I see that we get a little bit of an issue. Counts passed in as a positional argument. What are you saying? What are you complaining about here? Did I miss a comma? First argument must be string or compile pattern.
Is it referencing the star as the count flag and not just the character itself?
It could be. There it is. Good catch. Clean string. So now we run that. Okay. Now, when we look through this clean string, let's go ahead and see if we can find some sort of count. So let's say clean string dot index of, and see if we can find this star. Yep, that's not it. I think that's the correct function. Yep. My pure Python for string manipulation is rusty. Let me go ahead and do a little bit of research here. So let's say find index of a value within a string. It is index. Specify substring. Substring not found. Oh, got it. So it's just saying it didn't find the substring. It's not that there's an issue there. It's that there is no substring. If I pan in something like A, I'm sure it's able to find an answer. But if we look for the star, it actually returns that there is no star anymore. Right? Whereas if I were to look through text, it would be able to find that asterisk pretty quickly. All right. So we got one done. We were able to remove that star. Now let's go ahead and try to remove that hyphen. What I'm going to do is I'm going to actually wrap it inside of these conditionals there. And I'm just going to do a little bit of grouping. So I'm going to remove some commas. Maybe remove a couple of periods. Some question marks. We talked about that pound symbol in there. We also mentioned that there were quotation marks that were identified. All right, so that takes care. Oh, and then that slash. Almost forgot that slash. And we'll worry about this hyphen here shortly. All right, well then grab the clean string afterwards. And print the clean string as well. That way we can see both of them. All right. So the first thing we see is text. Still has all of our fire emojis. We can see that it has the ampersand. A bunch of periods are still being included. All those stars. I want to take a look at the scrollable element here. All right, so here's the end of our story. Now we start seeing the clean text showing up. The clean text no longer has the ampersands. I'm not seeing an instance of any of those periods. It looks like double quotes were still able to make it through. So we could address that here shortly. Let's see if it had made it through on both ends. Okay, so it did. So it looks like double quotes weren't able to make it through. And it looks like we still have that dash. Also that fire emoji. Let's get rid of that fire emoji because I think that's going to be the easiest one. And say UTF code for fire emoji within Python. All right, so here's the UTF code for the fire emoji. So I could just grab that and include it as well. All right. Just gonna worry about clean string now. Now we can see the fire emoji is gone. And see, I just now realized that we also have a semicolon, so I'm just gonna add that to the list. Yes, I am. I know I am doing these manually, right? Ideally, there's probably some sort of shorthand like \W that can identify all of this information and just immediately match it so that we could remove it. All right. Well, now here we see this these quotation marks have still made it through. Let's see if we can remove these quotation marks by adding the escape character. Okay, so quotation marks are still making it through. So there's something that we have to address. And so let's add a list here. And we know that we still have dashes. Well, let's see how we can divide these, right? Here we have our regex that we have created over so far. But we are having trouble just finding the ability to remove quotation marks. If I play this a couple more times here, we can see that the quotation marks are still being identified. So let's look it up here. Let's say regex that will identify quotation or quotation marks. All right, so here we can see an AI overview that's coming from Gemini. It looks like it's saying there's a problem within the grouping there. Here we can see that it gives me a separate pattern for being able to find information. So here's the pattern that it gives me. Let's try that out. It doesn't seem very different from the pattern that we have down below. But let's say that we add it here. We say quotation raw. We add our raw string there. And there's our raw string being appeared. Well, there's our clean string before. Let's add it again. So let's say clean string is re.sub, where we're passing the quotation raw, removing it, And we'll do this to the previous state of clean string. Okay, we run that through. It looks like what's going on here is these quotation marks aren't being identified as quotation marks. They're being identified as special characters. So you can see that's not actually just a quotation mark. That's not the regular double quotes that comes in. So now we're running into a special issue here. So to identify a double quote character in a regular expression, you simply use a double quote itself. Da, da, da. Okay, we could remove this and try to do it this way, but I'm pretty sure that's not going to work. Yeah, so it looks like we'll have to find a different way to address that because that's not regular quotation marks that are coming in within our text. Right? So we don't necessarily have to worry about that. That will get taken care of once we get deeper in and we're working within tokenization. All right. Now, the next thing that we still realize is that we have this dash. Well, let's see what we can do to actually remove this dash. Let's try to add it into our pattern here. Okay, seems like the dash is still making it through. And more than likely, it's for the same exact reason. You can go ahead and add that backslash just in case it's identified as a special character. It is not identified as a special character. This is likely due to the cost that this isn't an actual regular dash that's coming straight from the keyboard. It's likely just a special icon that was generated whenever this full stack quest markdown was generated as well. So we won't be able to just identify it within our string parameter unless we have the actual UTF code for it. All right. So now we were able to clean our string. We created a raw string. That raw string then got fed into our clean string where we substituted information. We put the raw string and the text, and we're able to see a little bit of clean string afterwards. All right. Does anyone have any questions over how we utilize regex to clean this text? Let's hear it, Nick.
Why did you ors between each string?
Why did I what?
Put the ors between the items in there?
Oh, got it. This is just because I utilize grouping. I'm making it an exclamation point or I'm making it explicit, saying that, hey, these are the patterns that I'm trying to identify. I could definitely do it where I could remove the ors and just have it all smashed together because then it would just match every pattern of that character. Um, but in this case, it was just my own decision to do it in a way where I grouped it with those parentheses on the outside and then divided it with the or statement. Does that answer your question?
Yes. And one more, is there a way to open the markdown so you can see the raw, I guess would be UTF-8 or whatever format it's in to get the values so we can write a regex string that actually gets rid of those dashes, quotes?
I'm so sorry,
Similar
Nick.
to how you did the emoji. See how it's
I think you're
dying?
you're breaking up on me and I'm not able to fully understand your question. Can somebody relay what he's saying if you're getting his question clear on your side?
I think he's asking, just like the same way you did define the fire emoji, just look up the Unicode for the dash in Google and paste that in and see if it works.
Got it. Yeah, there's definitely a way to do that. It's just that I know that later on I could leverage everything else that we're going to be doing within the process of this text pre-processing. So I don't necessarily have to worry too much about that one character or those one, two, or three characters that we're actually able to make it into the string, right? I want to clean it 90%, but I'm okay with having a little bit of still nastiness working within there for noise. Does that answer your question, Nick?
Yes.
Okay. All right. Awesome. All right, so now we have this information. We were able to clean up our string utilizing regex. Let's take a look at a couple of other examples. Oh, that's not it. Let's say that we wanted to remove some HTML tags in regex. Let's say I have my HTML noise. And here we're just going to utilize the simple division that says hello. And then we'll go ahead and close off our division. Well, I can now have clean text by utilizing re.sub, where we are going to pass in a raw string, where we know we're going to have an opening caret. We may or may not have some form of closing tag there that says div. That's a division I'm trying to remove. When it finds it, I just wanted to replace it with empty text, and I want to do this to HTML noise. I can take a look at clean text now. And we can see that hello is the only thing that comes back. If I had something like multiple exclamation points, and I only wanted to keep one, I wanted to keep some sort of punctuation. Let's say over expressive, where we have something like hello. Well, I can create a regex that says re.sub, where the raw pattern that I'm looking for will be of an exclamation point, where there is 2 or more. Let's go ahead and say 2, 9. And what I want to do to this is I want to replace it with just 1 exclamation point. Now I'm going to do this to over expressive. And then take a look at the clean text. Well, now we can see only 1 was returned. That's happening because it was able to find a pattern of 9, and then it found 1 more out there. So we did kind of clean it up, but it still found that it was too much. Right? Ideally, somebody wouldn't put in that much or that many exclamation points, but we cleaned it up to the point where now instead of having all of those expressions that are going to be fed into our model or the remainder, now there's only 2 of them. So still a win on our side as far as cleaning up the text. Go ahead, Nick. And let me open up the chat just in case something's coming through the chat.
They were just making fun of my internet. S- can you get the 9 after the comma and just leave it blank? I think that matches like 2 or infinite.
2 or infinite.
Daniel taught me that yesterday.
Perfect. Awesome. I am homeless and all right. I see the chat is it's just some fun stuff going around. All right, everyone. Well, now that we cleaned up our text a bit, let's go into the process of tokenization. All right, we broke all this up, but why did we break it up? And let me actually bring this block of code here down. I'm actually going to bring these up just so that those values are overwritten. A little bit earlier. Let me go ahead and restart my kernel there and run all. Okay, that failed. Why did that fail? Because I haven't imported RE. No problem. All right. So now we broke up everything. We can go into the process of tokenization, being able to break down this entire string of a story into something that's more feasible, something that I can work with, that is shorter and broken down into smaller steps. Now, we could go through the process of doing this ourselves, maybe utilizing something like split or trying to figure out what exactly differentiates a word. We could build a whole function that can do this process of tokenization. But because it's so common inside of language, inside of natural language processing, we're actually going to utilize something called NLTK, which stands for Natural Language Toolkit. Now, NLTK is a library, nltk.org, I believe. Let me see if that finds it. Yeah, NLTK is a library that is utilized specifically inside of the natural language processing portion. And it comes with a lot of different functionalities already pre-made for us to work with. And we're going to be inside of NLTK pretty much the remaining of this class for today. Now, we're going to import NLTK, but because there's such a massive amount of information in NLTK, it is not designed to where we could just import it and then use everything all at once. We actually have to bring in NLTK and explicitly tell NLTK what portions of its program we want to utilize. So there's going to be a bit of installation process here. And just so everybody knows where to find this bit of information, I'm going to go ahead and share this in the Avenger questions as well, so that you guys have a link to this portion of the curriculum. All right, let's go into the installment of NLTK. You'll see here that the interpreter that I'm utilizing inside of my main.ipymb or my Jupyter notebook is .default. You also notice down below that the virtual environment that I have activated here is .default. I'm using the .default environment that I've activated in my terminal to install NLTK. So I'll do so by running pip install NLTK. So again, first install NLTK, second install NLTK modules. All right, so for me, it's giving me a little bit of requirements already satisfied. For you guys, it's going to install an LTK for the first time. But again, this isn't going to give you everything that you need. I'm going to actually enter a Python interpreter here, or actually, it's better to do it inside of Jupyter Notebooks. So let's do it in here so that it's on record. I'm going to actually grab NLTK. So import. And from there, I'm going to run nltk.download. This is where I specify what is it that I'm trying to download. Now, because we're going to be using a tokenizer, what I'm going to download is going to be Punk T. We run that. We can see downloading package. And finally, this function here, or excuse me, this method of download Punkt T returns true, meaning that I am now able to utilize the tokenizer module. And now let's go into tokenizing text. Currently right now, my entire story is saved inside of clean string. But I want to break it up. There's a couple of ways of doing so. I could do so breaking it up by sentences. And I actually think that the fact that we removed all those periods may cause an error for sentences, but let's try it out. So I'm going to say from nltk.tokenize, I want to import sentence tokenizer or sentence tokenize. Now this is just a function. This function will iterate through the entire story and return a list of sentences within the story. So I can say sentence story and make it sent tokenize, where we pass in all of our clean text. And we can see that worked. Let's go ahead and take a look at our sent story there. So it looks like we're just getting hello. Let me see what's going on here. Oh, it's called clean string, not clean text. All right, so here we see a massive list, and it's true because we removed all the periods and exclamation points. Well, now it's confused. It's not able to divide it the way we want it to. Let's bring back a couple of those periods. Let's bring back these, remove both of the period and question marks there. All right, let's go ahead and restart our kernel. Let's execute all in order. And now we get it broken down by each independent sentence. Nice. Well, this is breaking it down by sentence. What would it look like if I wanted to break it down by word? Again, from the NLTK library, there's a module named tokenize that holds a function of word tokenize. Well, now I can say word story, where I can pass in the word tokenizer, pass in our clean string, and take a look at the word story. So that breaks it down. Now we have a list of my entire story where every single word is separated into its own index. You'll notice that when we use word tokenize, though, periods and special characters, such as that dash, I'm trying to find some sort of question mark in here. Well, you'll see that all of those are being identified as their own separate words. They're not being included into its previous word. All right. Now this is good for me because now I have the ability to either tokenize words by an entire sentence, or I can tokenize words by just the word itself. Again, this is coming from NLTK. We can see a couple of examples here, and it gives me an example usage portion. Actually, there's one here specifically for the tokenize here. You'll see there's a sentence, tells me it's utilizing the word tokenizer, and it breaks it down into small chunks. We'll talk about this POS tagging later on during part 2 of our lecture. All right, at this point, does anyone have any questions over how to utilize regex to remove noise and why we're actually utilizing the tokenizer, or how to utilize a tokenizer from NLTK? Perfect. If there aren't any questions, I'm going to go ahead and pause our lecture here. All right, welcome back, everyone. Now that we have our Zoom features here, or excuse our Zoom features, now that we have our text broken up and tokenized, we can work to the next process of our text processing here, which is going to be getting to our removal of stop words. After removing our stop words, we'll start talking about stemming and what lemmatization looks like with POS tagging. So again, stop words. What are stop words? Stop words is in reference to all of the words that really don't bring much context to the model for it to learn, such as and, of. I think we actually have a couple of examples for stop words. Let me see if I can find it here. Yeah, stop words. So we have the, is, at, on, in. They don't really bring much information over to the model. It doesn't really help the model learn in any essence. So we're going to actually remove said stop words, but I don't want to have to type out all these stop words from scratch. Well, I don't have to type out all said stop words from scratch because stop words are actually stored within NLTK. They are stored by language and can be grabbed through a method. Well, let's go through the process of actually grabbing these stop words. So again, it's inside of NLTK. Well, let's try to go through the process of importing it. Oh, excuse me. So this one is going to be corpus. Let me see earlier. Okay. Let me go ahead and walk through us here, because earlier we only installed or downloaded corpus inside of NLTK, and now we're going to need stop words. Awesome. All right, so we know we're going to need stop words. Again, I'm going to import NLTK here. And now I'm going to grab nltk.download stop words. And this is what will actually give me that stop words package so I can utilize it inside of my program. Well, now in order to utilize it inside of my program, it looks as such. I can go ahead and say from nltk.corpus. I want to import stop words. And I can load these stop words through stop words. Again, this has a method where I can grab it by language. This method is named words, and the language that I want is English. But let's take a look at what stop words looks like. Oh, I have a nice little typo there. Let me try that one more time. All right, so type words returns a readable list, but it actually returns a weird object that doesn't necessarily work very well with us. This is just kind of like their representation method, returns it as a list. So for us to work with it really well, we're going to actually turn it into a set. And by turning it into a set, we can interact with these stop words to change all of our tokenized information. So now we have our stop words available to us. When I want to remove them from the tokenized story, let me scroll up here so I can figure out what our variable was here. So here's our word story. That's the one we're going to go ahead and concentrate in cleaning up here. So I'm going to say word story, no stop words, or just say no stop. And I'm going to utilize list comprehension, where I'll say word for word in word story. if word not in stop words. I'm essentially checking if the word is inside of stop words. I'm not going to add it into this new list here. And if it isn't, then I'll go ahead and add it. And now I can go ahead and take a look. I can print word story. And I could print my word story, no stop. All right, so here we can see a little bit of a difference. So here we have the full stack quest, a tail, and then we have of, which has now been removed. It's not letting me grab it. All right. And as we continue scrolling down, we'll see more and more words being removed because they're considered stop words. Luckily, a very simple process thanks to NLTK. We were able to just grab the stop words module, import the words that we wanted by specifying that we want the words in English, churning them into a set. This allows us to utilize list comprehension to create a new list where all of our stop words have been removed from our story. All right, does anyone have any questions regarding stop words? Perfect. If no one has any questions, let's start talking about stemming, which is again removing all of the prefixes, or excuse me. Let me go ahead and make sure that I know what we're removing here. Oh, yeah, removing prefixes or suffixes. Moving prefixes or suffixes. And this is in order to give us words at its purest form, or attempt to grab words at its purest form. Well, just like everything that we've done, we could write a program to be able to identify what a prefix and a suffix is. We could then feed every single one of our words through it, and then try to identify what has a prefix and a suffix, and return the value of said word without the prefix and suffix. But again, this has already been done to us, or has already been done by NLTK, utilizing something called order stemmer. So we can import order stemmer from NLTK and utilize list comprehension to iterate through the list and stem each word in word no stops. So let's do that here. I'm actually going to grab this because I know I'm going to forget it. Okay. Now from an LTK, because we want to utilize stop words, oh, excuse me, because we want to utilize interesting. We may not need it, actually. Let me try it out. I think stemming might already be available to us. No, it won't be. All right, so we need to grab stemming from something called WordNet. So again, we'll do a different download here. So we'll import NLTK and then say NLTK.download. And we'll grab WordNet, which is what gives us access to this Porter stemmer. Well, now in code, I can actually say from NLTK dot stem, I want to import Porter stemmer. That is a class, so I need to actually create an instance of said class. And then I can just stem my words. It's a stemmed words is equal to stemmer. This is an instance of a class, so it has a method named stem where we can take in a word for every word in word story with no stop. Now we can print both of them to take a look at the difference. So now we're stemming each word. So here's the word story for with no stops. That's the second one. And then the first one is the stemmed words. You'll notice that all of them have been flattened now. That's happening from the stemmer. You'll see that dragons has turned into dragon. Wizards has turned into wizard. This is becoming has turned into become without an E. So there's no longer a valid word. Dreamed turns into dream, and so on. Again, Porter stemmer, very straightforward. So it doesn't actually have too much of a capability to break down each word to its exact value, but it does a pretty good job at giving us a 90% answer, right? It's going to be correct and give us pretty good words as to what each word means, but it will be making mistakes at possible stopping points. So that's a Porter stemmer. Now you may think to yourself, well, what's the whole point of utilizing Porter stemmer if I already know it's going to give me, it can possibly give me dirty data that's not going to work? Well, Porter stemmer is just essentially more efficient than using something like lemmatization. When you're utilizing lemmatization, you have to truly interact with each individual word. There's all kinds of nested functionality that happens inside of it. So it ends up just taking more time to actually lammatize text versus where stemming text is a little bit more quick and efficient. All right, so that's the difference between stemming and lammatization. Lammatization is going to break down the word to its very true meaning, whereas Porter stemmer is just essentially going to remove the stems of the word and return to you the root where that word came from. All right. Does anyone have any questions regarding stemming? Perfect. If no one has any questions, then let's start working to lemmatization. So lemmatization. All right, so lemmatization will be imported from NLTK dot, and I believe in this case it's still stem. Let me make sure. Yep, dot stem. And we will be lemmatizing through a concept, or excuse me, a class named word net lemmatizer. Now, keep in mind that a lemmatizer by default will treat every word as a noun. And this is a very important key factor there. We're going to see why here shortly. So again, we create some code. We go into importing our information. So we'll say from nltk.stem, I want to import the WordNet lemmatizer. I want to create an instance of it. So lemmatizer, it's going to be WordNet lemmatizer. All right, once I have my instance, well, then I can iterate through a list. So I can say lemmatized text can be equal to a list comprehension, where we'll go through the lemmatizer, which is an instance of a class that has a method called lemmatize, where we're going to lemmatize each word for every word in our story. Let me grab that story name here. Word no stops. And again, let's print both of them. Let's say we want to print lemmatized text, and let's print word no stop. So it looks like we're getting an error from lemmatized text.
Yeah,
Lemmatized.
misspelling and right before the print statement. Lemmatized instead of lemmatized.
Thank you. All right. Well, now when we execute this, every word did in fact get lemmatized. But if you take a look at every word here, it looks like it's exactly the same. Nothing has changed. It looks like an S was removed from towers. So it looks like it gets rid of pluralization by default by treating everything like a noun. But it doesn't really break down the word much more than stemming did. Well, how do we fix that? All right, how do I tell this program that this isn't a word? This actually needs to get tagged with some sort of part of speech portion. So the lemmatizer a lemmatizer treats all words as nouns. And it makes it pretty much almost impossible for the lemmatizer to actually identify the true meaning of the word. Without having a part of speech tag. Well, what is part of speech? So part of speech is in reference to whether we're talking about nouns, verbs, adjectives, adverbs, pronouns, prepositions. All of those tags are important. And let me just do that here. So we have nouns, verbs, pronoun, adverb, adjective, and prepositions. So now every word belongs to each one of these groupings, and we need to tag them so that when we pass it in to the lemmatizer is able to identify, oh, this is a verb. Well, let me break it down and treat it as a verb. Well, how do I do that? Well, the lemmatizer already has something called POS tagging. And again, we're going to need something else from NLTK. I'll go through the process of going import NLTK. I'll then call nltk.download, where I'm going to pass in the averaged perceptor or perceptron, I'm sorry, tagger. And this is what gives me the capability to work with POS tagging. Now let's talk about what POS tagging actually does. Here's my code block here. I'm going to, from NLTK, bring in my POS tag. Oh, there you go. Not the time for pop-ups. I'm going to import the POS tag. Now the POS tag is a function. Let's take a look here. We're going to say tagged words is equal to the word story with no stops. And then I want to see what tagged words looks like. Oh, forgot the POS tag. Was that what you were about to tell me? Okay, I see head nods there. All right. Well, now when I do this, the POS tag is actually returning some sort of tagging assignment. But this doesn't necessarily fit what I want it to, right? Because, well, like I said before, we're looking for nouns, adverbs, verbs, etc. And all of these are tags with JJ and N. These tags are a little bit different than what I expected to see. Well, that's because of the type of tagging that we are doing. So the POS tag utilizes a tagging system that doesn't necessarily match the lematizer tagging system, but it does get us 80% of the way there. So now we ourselves have to create a function that will properly tag each word to match the tag system that a lematizer is utilizing. Well, now in this function, what we're looking for here is called word net. So here we'll go say, oh, excuse me. I'll import from NLTK dot corpus the word net. Now, WordNet is different than stop words, right? What WordNet actually brings into us is the ability to tag a word with an actual tag that will match what our lematizer is looking for. So now we can create our function. We can say get WordNet POS, which is our part of speech tag. And what we're going to take in will be our NLTK POS that was already assigned, right? So this is the NLTK POS that gets automatically assigned. And we're going to go ahead and pass that in to our WordNet, or excuse me, to our get WordNet POS function. Now this function is pretty easy. We'll say if NLTK POS dot starts with, we're just checking the very first letter. If it starts with a J, well, what we're going to be returning then will be the WordNet dot adjective. So now for every single one of these that starts with the J, so for example, ancient is actually going to be tagged as an adjective. Here we see pierced. This will be tagged as an adjective as well. Young will be tagged as an adjective. Now the POS tag system, you'll notice something like pierced, right? Pierced could also be a verb. How is it able to identify that this is an adjective? Well, what the POS tag system does is it's actually utilizing a trained model that will run your words or your entire everything that got passed in as an argument into a, I don't want to call it a learning model, but essentially it's an algorithm that can utilize context clues depending on everything going on inside of the sentence or the story to determine what these words actually are, whether they're being utilized as nouns or adjectives. And that's the entire purpose between utilizing POS tag. It's very accurate. at giving us a close guess as to what each word is actually representing in regards to part of speech. We can continue here. We can say if NLTK POS starts with a V, well, this will return the word net dot verb. If NLTK POS starts with N, this will return the word net dot noun. If NLTK POS starts with R, then what this will return is an adverb. And then finally, everything else, if it does not match the different variables that we have here, it will get treated as a noun. Now, I could probably make this a little better. There's really no point in having this portion here if it's going to be my else statement. So I could refactor this code a little bit, but we'll dive into that later once we still have some time. Let's hear it, Carlos.
Sorry, right there on the return for noun, you put word ner. Sorry, in the if, nothing else. There you go.
Thank you. Appreciate it. All right, so there's our function. I'm going to actually make sure that this function is defined properly. Great. So now again, we're going to pass in one of these words. These words have already been tagged, and we have them as tagged words. Let's go ahead and take a look at what tagged words index 0 looks like. Well, tagged words index 0 is a tuple. Now, this tuple has both the word and dt. What we need to pass into this wordnet function or into this wordnet POS function is index 1. All right, because that just gives us dt. So now we can call the function of get wordnet POS. You'll see that that returns n for noun. And that's what it expects the tagging system to work with. So that's the way we were going to pass it into our lamentizer. Now let's work through the process of passing it into our lamentizer. And I'm just going to bring up that tagged words here. I'm going to do index 0, just so we have that visualization of that tuple. Well, how do I break this down? I just did all this process. What's the difference in my lamentizer now? Well, I'm still going to call lamentize text. I'm actually just going to take this exact portion of code here and bring it down below. But I'm going to change it just a little bit. All right, so lamentize text. Again, our lamentizer can take in up to 2 parameters. So let me make sure that it's annotated here. So the lamentize method takes in 2 parameters. One, which is required, is a word to lamentize. 2, which is optional, is the wordnet POS tag. All right, so now we have our first argument and our second argument. Let's change this so that our lemmatizer can work. In a way where we can actually pass in both of those required arguments. Well, as of right now, I'm iterating through this word story node stops. That's not what I want to iterate through anymore. Now I want to iterate through tagged words. Because we know tagged words is what holds our list of tuples. Where in index 1, we have the word, so we can even divide this and say for word, comma, tag, right? Because in index, in index 0, we have the word, and in index 1, we have the actual tag. So now we're doing a little bit of destructuring with this tuple here. And again, there's two separate arguments or parameters that can be passed into the lemmatized method. Currently, I'm passing the requirement 1, which is the word. How do I pass in the second requirement?
On a tag.
Okay, let's go ahead and do tag. Now, is this the tag that I want to pass into the lemmatizer?
I don't know. Run it. Let's see.
Yeah, let's see it.
You want to throw it into your if-else function thing that you made?
That's right.
I do, yes, but let's run this here and see what comes up. All right, so when I run this here, it's giving me an error, and it's telling me 11 times words by the shortest the possible. So here it's saying, hey, you're giving me a POS tag, but this POS tag that you're trying to give me doesn't exist. I have no idea how this works. And that's because it's an incorrect tag, right? This POS tag that we currently have belongs to NLTK, not to WordNet itself. So we need to feed it to our function of get WordNet POS. Let me go ahead and pass that in there. And then pass in our tag as a parameter. And now when we run it, we get our lemmatized text. Let's go ahead and print our lemmatized text and print our, ooh, I don't have that story anymore. Let me grab it from above. Word story, no, stop. Keep forgetting what I named that variable. Now we run it. We can see that our lemmatized text and our word no stop has changed a bit. So for example, towers is now tower. Pierce still remained as pierced. It works different than stemming, right? Whereas stemming would have just turned that into pierce. There's sky and the difference of skies now. River instead of rivers. Flow instead of flowed, and so on. Now, because there's a little bit more interaction, both in building this function or building a workable way to work with a lematizer, I'm also iterating through this text a considerable amount of times at this point, right? I iterate through it to clean it from regex. I iterate through it to tokenize it. I then iterate through that text one more time to remove all stop words. I iterate through the text again to attempt to lemmatize the word. But as I'm trying to lemmatize the word, I also got to tag it. So I iterate through the entire text to tag it first. Then I go into lemmatizing the word. But as I'm lemmatizing the word, I have to tag it an additional time with a completely different tagging content. So at this point, I've iterated through the text or made actions to the text at least 5 or 6 times. And that's for every index inside of your text file. So you can see how if you're working with a large amount of text, this can be pretty consuming for a machine as far as efficiency. And that's the key difference between lemmatizing and stemming. Right? If you're trying to decide which one to utilize, it's just really which one is it that you're heading for? Are you looking for accuracy? Are you prioritizing accuracy over efficiency, or are you prioritizing efficiency over accuracy? That's the real difference between lemmatize and stemming. All right. Does anyone have any questions regarding stemming? Perfect. Since there are no questions, let me go ahead and stop our recording here.